A very good day to all my lecturer, TS Dr. Siti Asma binti Cik Aziz, and to all my fellow friends. So today we're going to present our PBL, which we call Project-Based Learning. So the topic is given is the silent C. So we're going to discuss about that. So before that, let me introduce my team members. So me myself is Nanda. We have Alaina and also Emily. So this is the content that we have, our lecturer has given in our PBL. So we have task A, task B, and task C. So I'll be presenting task A, which is the SSB advantage. So let's start from task A first, my part. All right, so this is about the introduction. So before we understand the advantage, so let's find I understand what is SSB. What is SSB means is a single sideband actually means. So as we know, single sideband is a derived from the conventional AM modulation. So in a normal AM signal, there is three components, okay, that are transmitted. So first is carrier, second is upper sideband or USB, we call it as short form is USB. Third is lower sideband, which is LSB. So both sideband is actually contains the same information while the carrier itself does not carry useful information. Its main purpose is to help during the signal transmission and also detection. So now this SSB single sideband is actually works differently. Instead of transmitting all these three components, SSB will suppress and remove the carrier and also only transmit only one sideband only. Okay, so that is why we said here we have three, like I said, a carrier is transmitted, upper sideband and also lower sideband. So now we're going to move to the next slide. So this is the next slide, which we're going to explain about the advantage. So first, we're going to explain about the bandwidth efficiency. So take this is the first advantage of SSB, which is bandwidth efficiency. Okay, so before we compare with SSB, we need to understand how this bandwidth is calculated. Okay, for this example, the voice bandwidth. Okay, this we take the voice bandwidth is given the highest modulating frequency, which is 3.4 kilohertz. So for the conventional AM, the bandwidth is given the formula which is equals to 2 FM. Okay, so you replace and get, and you will get 6.8 kilohertz. So we will go deep this formula. So BW is bandwidth, FM is modulating frequency, and you can see there. So the reason why we have to times with 2, you can see why 3.4 we times with 2 is because the conventional AM signal transmit two sidebands. Okay, we transmit two sideband. So means we get 6.8. So means the conventional AM signal requires 6.8 kilohertz of spectrum to transmit the voice signal with a bandwidth just of only 3.4 kilohertz. So in other words, to easily understand this concept, AM use twice as much bandwidth because it transmits both set, which is upper sideband and also lower sideband. All right, so we're going to move to the next slide. All right, so this one is the bandwidth efficiency. So for the single sideband, we have the comparison. We have do the comparison. Okay, for this one we will compare. So the formula for SSB, as we said, is FM. Okay, so as we know in this example, we have taken that the voice bandwidth is 3.4 kilohertz. So therefore, the bandwidth for single sideband is 3.4 kilohertz. So now let's compare with the two system, which is conventional AM. So when conventional AM, we have to times with 2, like just now, we get 6.8 kilohertz. So for SSB, we only get 3.4, but for AM, we get 6.8. We have to times 2. So in other words, to easily understand this, SSB is actually single sideband actually reduce the bandwidth requirement about 50%. So this is very significant improvement because radio spectrum is actually very limited and must be shared with many communication system. So that is why we need a very lesser bandwidth. So from this comparison, we can clearly see the difference that the conventional AM is required 6.8 kilohertz of bandwidth. However, single side band only needs 3.4 kilohertz. However, although both system they transmit the same voice information, even you say A, the word transmit over there is A, but SSB only achieve this using half the bandwidth. So this is why we consider a single sideband is much more bandwidth and it is much more efficient compared to conventional AM. All right. So we're going to move for the next slide. So the next one is okay. This is okay. So like we said, SSB has more smaller bandwidth, less noise, less interfere, and also signal becomes more clear. Okay, it's the same slide from just now. So we're gonna go for the power efficiency. So this power efficiency is actually what we understand is that the second advantage of the SSM. So besides we have bandwidth, SSB is also transmission power more efficiently compared to conventional AM. So to understand this, let's look at the first conventional AM formula. So we have the carrier, we have the upper sideband, and also we have lower sideband lah. Okay, so however, only these two sideband carries the actual message or information. The carrier does not contain any information. Its purpose is only just to assist the modulation and the demodulation process. So even though this carrier actually don't have information, but it is still we consume, we still use, but in a large amount of transmission power. So that is why we say the most power in conventional AM is the wasted in the carrier. It's just waste. Okay, that's waste. That's why we don't recommend to use it. Okay. So we're going to see the explanation from this formula. So you can see PT actually stands for total transmitted power, PC is carrier power, and M is the modulation index. So when the modulation index range is from 0 to 1, when M is equals to 0, there is no modulation. But when M equals to 1, the signal is 100% modulated. So what is 100% modulated means? It means the maximum modulation without distortion. So for example, we assume M is equals to 1 because it's a fully represent. So when we substitute 1, and you can get the power is 1.5 PC. So this means that total transmitted power uh, is one and a half times the carrier power. Okay, so this result actually tells us that transmitter must generate 50% more power than the carrier power alone. So however, not all of this power carries all the useful information. Okay, even we can see, even they said a large portion of power is still used by the carrier, even though this carrier actually does not contain even message. So why we want to waste this large power? Okay, and hopefully this calculation makes you guys understand. All right, so next we're going to move for the next slide, which is the power efficiency. The same thing, we're going to compare with the we could just this one, this example, the carrier power is 100 watts. Okay, and the modulation index, we said it is 100% from the question. Okay, so from the previous slide we learned that the total transmitted power in AM, okay, we have replaced and all, so we replace this formula, so we get 150 watts. So this means the transmitter must produce 150 watts of total power. So I want to explain where this 150 watts will goes. So now we'll take a look over here. We have 150 watt is actually distributed. So out of 150 watt, only 100 watts is used by the carrier. Only 100. So where goes this remaining 50 watts? So this remaining 50 watt, it is shared equally between the upper sideband and lower sideband. Okay, you understand it? So when we add it together, 100 watt plus 25, you'll get 150 watts, which matches our total transmitted power. So this is where we can explain why that is inefficient. Why we say this is inefficient? Because just imagine, the carrier uses 100 watts, but it does not carry any information. Okay, only two sidebands carry the voice or any message signal that we send, either we send any message. That means out of 150 watts, only 50 watts is actually used to transmit this useful information. So this remaining 100 watts is actually about two thirds of the total power it's consumed by the carrier. So this shows this conventional AM is not a power efficient. Okay, we are comparing with the power efficient. So this is not a power efficient because it's most of it the power does not transmitted, and it's not contributed any sending message. So hopefully this understands you the okay. So we're gonna explain about uh all right, so this one we're gonna explain about SSB is widely used for a long distance communication. Okay, because it uses both bandwidth and also power more efficient compared to conventional A. So as we learned before this, so this one we're going to go for the SSB provides several important advantages such as less wasted energy. Okay, so as we know, last time we discussed AM in conventional AM, a large amount of power is wasted on the carrier, even though the carrier does not carry any information. But in single sideband, the carrier is suppressed. So this means almost all the transmitter power is used to send the actual message. Okay, so since less energy is wasted in single sideband, so it is much more efficient compared to AM conventional for communication. Okay, for the second point, I can say better receiver sensitivity. So this one, the receiver sensitivity means the receiver ability to detect very weak signal. So because the single sideband has a concentrate the transmission power into one sideband, so the receiver will receive a very stronger signal compared to conventional AM. So the third one is transmitter power concentrated into one sideband. So this point is actually, so instead of dividing into the power between the carrier upper sideband and lower sideband like conventional area, conventional AM, SSB single segment is all places almost all the available powers into one single segment. So this is means it's a very useful information has been transmitted with a greater efficiency. All right, so in this we have this one. So the first advantage we can see here is lower noise, which means single sidebands occupies a smaller bandwidth and the receiver collects less unwanted noise. Okay, and second one is better signal to noise ratio. So this one is signal to noise ratio. It compares the strength of the useful sign with the background noise, so it won't have any background noise. Okay, a higher signal noise ratio means voice quality is very clear and also it's easier to for communication. All right, so the third one is more effective transmission rates. So because SSB has lower noise and a better signal to ratio, the communication signal can even travel even much longer distance while still maintaining in a good quality. Later we will see the real world situation, okay, where we can use this, okay, this SSB. All right. Okay, so this one is our long distance communication lah. The next advantage of this lah. So you can see a single sideband we use it for military radio, aircraft communication, marine communication. So why we are using in aircraft? Aircraft is like we are using during the flight. The aeroplane want to contact to the flight air traffic controller for radar issues. Okay, so once they want to connect, when they want to speak to the air traffic controller, which is thousands of miles. So they use what? They use this signal. They use single sideband. So that is where they use this one. So the first advantage why we are using SSB in this long distance communication, as I said just now, it's a better signal range. Okay. Second, it's the communication is reliable communication. Third is common application. So like I said, aircraft communication uses SSB where the pilot can communicate with the air traffic controllers over hundreds of thousands of kilometers without any disturbance or noise. How about marine communication? So marine communication also use this SSB, okay, in the open ocean, okay, are very far because as you know, ocean is very, very far. So they use from the coastal station. So they use this SSB to connect with the coastal station. Okay, how about amateur radio? Amateur this sorry, military communication. So for what they are using, so they also relies on this SSB because it provides efficient and dependable long range communication lah. Because military, they will go for communicate to another military which is in a far distance, so they use this single sideband lah. Okay, so from this diagram we can shows that SSB can transmit signals over a much longer distance. So the transmitter sends the SSB signal through the atmosphere. So because this SSB use power is efficiently, the signal can travel much farther, as you can see. Okay, so why does this SSB travel further? Some people think SSB travel farther because he has more power. Actually, that's not the main reason. Okay, the transmitter power actually can be exactly be the same for AM and also SSB, but the difference here is that in the conventional AM, yes, much of the power is wasted. It's actually wasted. We are not using because it does not carry any information. But the SSB is almost all of the available power is used to transmit the information. So because more useful signal reaches the receiver, so the communication range is also has been improved. So it's like we just give a real life example, like imagine both of your friends, you are talking to each other but you are standing in a far away. So the first person spends more of their energy, you're shouting at your friends just because you want to speak to them. Okay, you want to speak any information, so by that time they say the message, they already get tired. Okay, because you are shouting. So when your friends is standing in a very far distance, you have to shout. When you shout and shout and shout, you'll get tired, and you can't reach the important message that you want to say because you are tired. So the second person second person also use all of this his energy to reply back to your message. Maybe he's sending important message or what. So even though both people use the same amount of energy, you're shouting, but the second message person heard more clearly. This is similar to how this SSB works. All right, so now we're going to go for the conclusion. So based on what we have discussed, we can conclude that this single sideband SSB modulation is much more bandwidth efficient than conventional AM. So the first reason is that, as we know, just I explained, SSB use less bandwidth. As we calculate just now, 3.4 kilohertz compared for 6.8 kilohertz. Okay, and also requirement just 50%. Okay, secondly, SSB also only transmit one sideband. Okay, so moreover, SSB uses smaller bandwidth and all. Okay, more channels can be feed. Okay, from this slide we can see. So another point we can say, it is less interference since each channel occupies less bandwidth. There is more space between neighboring channels, so reducing signal overlap, and also we can improve the communication quality. So overall, communication becomes more efficient as we save the bandwidth, reduce the interference, and allows more users to share the same frequency spectrum. All right. So to conclude, as I said, the same thing lah. Okay. So in conclusion, single sideband modulation is much more smarter and much more efficient modulation techniques because it saves bandwidth, it reduces power consumptions, improve a long distance communication. Okay. So thank you guys for your attention. That's I conclude for my presentation. Okay. So I will be ending here. So next is my next team member is going to present it. Thank you so much.
Assalamualaikum. My name is Siti Dr. Syarah Nabiti Jeffrey and my train number is D122410609. Today I will talk about Task B receiver design and synchronization. For this slide, I would like to talk about receiver block diagram. First, antenna, and then we go to the RF filter, and then we go to RF amplifier, and then mixer plus local oscillator, and we go to IF amplifier. Next, product detector and plus BFO, and also audio amplifier. Lastly, we go to the speaker. Now we go to the function in every of compartment. First, we go to the antenna. The function is receive signal. Second, RF filter. The function is remove unwanted signal. Third is RF amplifier. The function is strengthened with signal. And we go to mixer plus local oscillator. For the mixer, we convert signal to IF, and local oscillator is help stunning. IF amplifier is amplified IF signal. Product detector BFO is recover audio. Also, BFO is generates carrier. Audio amplifier is increased to the sound. And lastly, speaker is increased sound. Next, we go to the why carrier recovery is needed and why use BFO. Why carrier recovery is needed is for AM signal, carrier is transmitted and easy audio recovery. For SSB signal, carrier is suppressed, receiver must be generated by carrier. Why you use BFO? BFO is what? BFO is big frequency oscillator. The function is generates artificial carrier for demodulation. Advantage is simple design, accurate carrier recovery, stable synchronization, and low cost. Without BFO, distort audio, unclear speech. Then we go to the synchronization requirement. Receiver frequency must match transmitter frequency. BFO helps recover clear audio signal, prevents distortion and voice pitch changes, ensure reliable long-distance SR communication. Suitable for submission, high sensitivity, good noise rejection, long-distance communication, low power consumption, stable carrier recovery, and reliable for emergency channel.
And Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Amir Alwani, B2.1. The matrix number is B12241073. So today I will take on the class C, the FDM multiplexing plug. What is FDM? FDM stands for frequency division multiplexing. It allows multiple voice channels to transmit at the same time by assigning and a different frequency band to each channel. This to prevent the signal overlap and interference. As you can see, this is the objective: transmit 3 voice channels simultaneously, use SSB, modulation, and FDM. Each voice channel has a bandwidth of 3.4 kHz. So this is the chart that how the frequency division multiplexing works. Voice channel 1, voice channel 2, voice channel 3, FDM multiplexer, and transmitter. SSB transmit only one sideband, reducing bandwidth by 50% compared to conventional AM. It also improve power efficiency, making it suitable for a long distance SAR communication. What is SAR? SAR is search and rescue. For example, think of SAR as the emergency response teams at sea. When someone sends a distress signal, the SAR station communicates with the rescue team and coordinates the rescue mission. Therefore, it's a reliable communication system is very important to save people. That's why we need a reliable communication system. Okay. SSP transmit. This is the the comparison between conventional AM and SSB. Conventional AM it have 6.8 kHz bandwidth, while SSB have 3.4 kHz bandwidth. For conventional AM, it consumes higher power. For SSB, it consumes lower power consumption. And for AM, it's less efficient. For SSB, more efficient. That's why SAR use SSB for the communication system to the rescue team to coordinate the rescue mission. This is frequency allocation plan. As you can see in the picture, this is channel 1, 10 kHz carrier frequency, and the frequency range is 10 to 13.4 kHz. For channel 2, 15 kHz, the frequency range is 15 to 18.4 kHz. The channel 3 is 20 kHz, and the frequency range is 20 to 23.4 kHz. Each channel is assigned a different carrier frequency to avoid overlap. Guard band are provided between the channel, if you can see in the picture, between channel to reduce interference and ensure reliable communication. By combining SSB and FDM, the system can support three voice channels simultaneously while using bandwidth efficiently. These will improve the communication reliability during the rescue operation. In conclusion, SSB FDM allows multiple voice channels to be transmitted simultaneously while minimizing bandwidth usage and interference. Therefore, it's an effective solution for the SAR, search and rescue communication system. So this is the benefit that I have told you earlier. Efficient bandwidth usage, three simultaneous voice channels can work together, lower power consumption, and it can reduce the interference, and is also suitable for SAR emergency communication. That's all from me today. Thank you.